Inverse hyperbolic derivatives, section 6.9. Here we have some shortcut formulas for derivatives of inverse hyperbolic functions. Derivative of sinh inverse of x is 1 over square root of 1 plus x squared. Derivative of the Cosh inverse, 1 over square root of x squared minus 1, and so forth. So I'll derive some of these. Let's see, for part A, let's see, if we let y equal sinh inverse of x, that means that x is equal to sinh of y, and if we take the derivative implicitly with both sides, that means that take the derivative of y with respect to x of both sides. So so we have derivative of x with respect to x is 1, and for the right side we want to use the chain rule. So derivative of x with derivative of sinh y with respect to x is the same as derivative of sinh y with respect to y times dy dx, and then derivative of sinh is the Cosh, so 1 is equal to Cosh y dy dx, and if you solve for dy dx, that means that dy dx is 1 over the Cosh y, and then we want to express that in terms of sinh, because our original function was the sinh. This is y equals sinh inverse, so we can use the derivative of the identity Cosh squared minus sinh squared equals 1. That means that if we add sinh squared to both sides and subtract 1 from both sides, that means no, just add sinh squared to both sides. I'm sorry. Solve for Cosh squared. So that means Cosh squared is equal to 1 plus the sinh squared. So that's the one of the key identities here. So so that means that the Cosh is going to be positive. So that means that Cosh is going to be equal to square root of 1 plus the sinh squared. Okay. So that means dy dx is equal to 1 over square root of 1 plus the sinh squared of y. But that is just equal to x squared. Sinh squared is equal to x squared. So this is equal to 1 over square root 1 plus x squared. So that's the derives the formula for the sinh inverse. You could also use the expression of sinh inverse of the formula that we had derived before for the expressing sinh inverse in terms of the exponential function. So that's another way of doing it. So let's do it that way too. So if we do so method 2, y equals sinh inverse x, and that's going to be ln x plus square root x squared plus 1. So take the derivative, so that means that dy dx is going to be derivative with respect to x of ln x plus square root x squared plus 1. Well, this is a composite function, the derivative of the log is 1 over whatever we're taking the log of, so this is going to be 1 over x plus square root x squared plus 1 times the derivative of the inside function with respect to x of x plus square root of x squared plus 1. Then we take the derivative of that. So this is 1 over x plus square root of x squared plus 1. Derivative of x with respect to x is 1, plus, and this is going to be, derivative of this is going to be 1 over 2 square root of x squared plus 1 times the derivative inside there, so times the derivative with respect to x of x squared plus 1. So this is going to be 1 over x plus square root x squared plus 1 times 1 plus, okay, the derivative of x squared plus 1 is 2x, so we have 2x over 2 square root x squared plus 1. Okay, so let's get a common, well, actually we can cancel the 2's, then we can get a common denominator if we multiply top and bottom of this fraction by square root of x squared plus 1. So let's write this 1 over x plus square root of x squared plus 1 times square root of x squared plus 1 over square root of x squared plus 1 plus x over square root of x squared plus 1. Okay, so now we have we can add the two numerators because we have the same denominator. So we'll have 1 over x plus square root of x squared plus 1 times x plus square root x squared plus 1 over square root x squared plus 1. Okay, so so these two terms will cancel, and that just leaves us with 1 over square root of x squared plus 1. And that's the same thing as 1 over square root of 1 plus x squared. Okay. So that's another way of doing it. Okay, so okay, so I guess I'll do the Cosh inverse, and that's so the next one on the list, Cosh inverse of x. Derivative of that is 1 over square root of x squared minus 1. Okay, so if y equals Cosh inverse x, that means that x is equal to Cosh y, and I take the derivative, that means derivative with respect to x of x equals the derivative with respect to x of Cosh y. and that means that 1 is equal to, using the chain rule here, derivative with respect to y of cosh y times dy dx. And this derivative will be sinh. So 1 is equal to sinh y times dy dx. That means that dy dx is equal to 1 over sinh y. And then we can use the identity again we used before, cosh squared minus sinh squared equals 1. And if we solve that for sinh squared, it means that sinh squared is equal to 1. Cosh squared minus 1 is equal to cosh squared minus 1. So that sinh is going to be the square root of plus or minus the square root of cosh squared minus 1. Okay. But we're restricted to the domain here because remember the domain is restricted to the positive numbers, so this is going to be the positive square root. Okay, so this is 1 over square root cosh squared y minus 1. But cosh squared is just equal to x squared, so that's so it's going to be equal to 1 over square root x squared minus 1. Okay. Okay, so let's do the next one on the list is the hyperbolic tangent. Derivative that is 1 over 1 minus x squared. Let's see if we can derive that formula. Okay, so y is equal to tangent inverse x. That means that x is equal to hyperbolic tangent of y. It means that dx equals with respect to x of hyperbolic tangent of y. It means that 1 is equal to derivative with respect to y of the hyperbolic tangent times dy dx. And this is just equal to the such squared, the formula we had before, y dx. That means that dy dx is 1 over such squared y. So if we go back to the same identity we used before, the cosh squared minus sinh squared equals 1. If we divide by cosh, divide everything by cosh squared here, we get 1 minus the tanh squared is equal to the such squared. So this is going to be 1 over 1 minus the hyperbolic tangent squared y. And the hyperbolic tangent squared is just x squared, so that's equal to 1 over 1 minus x squared. Okay, so that derives the hyperbolic tangent. Okay, so the other proofs are going to be similar, and I'm not going to go through all of them. And let's see if we can apply these formulas. We want to find the derivative of hyperbolic tangent inverse of 2x. We can so we can apply the chain rule here. We want to use the rule for hyperbolic tangent, but replace x by 2x. So it's going to be 1 over 1 minus the quantity 2x squared. And then times the derivative with respect to x of 2x. We use the chain rule because the inside function is 2x. So this is going to be equal to 2 over 1 minus 4x squared. Here we have the regular sign in the hyperbolic sign. So we want to use the product rule, and so it's going to be sine x times the derivative with respect to x of the hyperbolic sine inverse of 2x plus hyperbolic sine inverse of 2x times the derivative with respect to x of sine x. Okay, so this will be, and here we want to use the chain rule. So the derivative of hyperbolic sine is 1 over square root of 1 plus x squared, but we put a 2x instead of an x there. So it'll be 1 over square root of 1 plus 2x squared. But then the inside function is 2, so take the derivative of that, of the 2x, that's going to be times 2, plus hyperbolic sine inverse of 2x, and the derivative of sine is a cosine. So that's, we can write these, we can put the 2 and the sine over in the numerator here. So this is going to be 2 sine x over square root of 1 plus 4x squared plus hyperbolic sine inverse of 2x times cosine x. Cosh inverse of 3x. So that here we want to replace x by 3x and then multiply by the derivative of 3x. So it's going to be equal to 1 over 1 minus 3x squared times the derivative of 3x with respect to x. And that's just equal to 3, so it'll be 3 over 1 minus 9x squared. Okay. Okay. Okay, I think that's enough. I have some other examples. I'll just leave them as exercises. So it's just here you use the formula for the derivative of cosine, and then you multiply by 2. Here you use the chain rule with the Cosh inverse and so forth. So I'll leave these as exercises, and I'll stop here.